Hello, this is part 3 of circular motion. I'm going to talk about the kinematics aspect of circular motion. Now that we have this variable to work with, which is theta, this is the angular position variable. Now let's use this to define angular velocity. And let's start with average angular velocity. Now, in the previous video, I told you what theta means. Let me repeat that. So we have this object going in a circle, and I want to measure my angles from an arbitrary axis. Let's say this will be your x-axis. And I'm here right now and doing a counterclockwise rotation about the center right there. This is the counterclockwise rotation, initial position, final position. The radius is r. This is theta. Let's call it theta I. Let's put an index there. And this one, theta final. And the difference will be delta theta. Theta final minus theta initial. Okay, theta is measured in radians. What is average angular velocity then? Well, this takes time to get there, right? Delta t. So why don't I divide delta theta by this time interval, delta t, and call this the average angular velocity. I'm not going to use v. Instead, I'm going to use omega, okay? Not the capital omega, the small cap omega, omega average. So omega stands for angular velocity. Numerator is in radians. Radians. Denominator, seconds. So the unit for angular velocity is radians per seconds. Okay, simple as that. Theta may increase steadily, which would mean a constant angular velocity. What about clockwise rotations? All right. Well, then theta final will be less than theta initial. So you'll have a negative number, okay? So omega itself has to have some sort of polarity, okay? That's why it is also a vector quantity. It is a vector quantity. Means we have to have a direction for it. So in this two-dimensional plane, the options are either counterclockwise or clockwise. Clockwise. So if I want to associate a direction to omega, then I have two options, right? Two options for directions that will correspond to two directions for rotation. Now the direction needs a vector, so a vector, a quantity with magnitude and direction, right? A vector. So what will be the direction of this omega? This omega cannot point in any direction on this two-dimensional plane. because you can rotate it anywhere you like, okay? Which one is the correct one? Instead, you're going to use a third dimension. So the direction of this omega vector, let's put an arrow on top of omega now. The direction has to be along a third direction, not x, not y, but a third direction, which is perpendicular to that plane. Okay, so we have to think in 3 dimensions right now. So why don't I try to draw this in 3D? So you have a plane here, a plane, which could be a sheet of paper, right? And this circle now will be on that plane. Now using perspective, I can draw it like this. And looking from above, it is a counterclockwise rotation, let's say. I'll put that arrow here. So this will mean an angular velocity vector in a direction which is perpendicular to that plane. All right. So that direction perpendicular, upward. All right. And the vector I need is this. Okay, so this will be my omega. See, I have 2 options. It's either pointing up or pointing down. Pointing down would correspond to rotation, which is clockwise, looking from above. Like, let's say you have another rotation here, but that is clockwise. Now this would have a vector pointing downward. That will be omega for this one. All right, now to remember this, you're going to use the right-hand rule. Okay, the right-hand rule, not the left hand, but use your right hand. Curl your fingers like this in the direction of rotation. Right now, this would be a counterclockwise, looking from above. Looking from the top, it will be a counterclockwise rotation. The thumb will tell you which direction the angular velocity vector points at. A clockwise rotation is like this, looking from above, and the thumb shows you the direction of the angular velocity. All right, so you have 2 options. It's either up or down for a plane which is horizontal. Any kind of rotation will give you on that plane a velocity, angular velocity vector, which is perpendicular to that plane. Right? This is 90 degrees. This is 90 degrees right there. All right? So that is the direction. What about the magnitude? Here's the magnitude. The magnitude is this. That's for average, though. What about the angular velocity at an instant, right? If you plot this as a function of time, if omega is changing, some arbitrarily like this, okay, you can look at a time interval, which corresponds to I and F. This is Ti. This is Tf. And you can find the omegas that correspond to those 2. This will be omega inish. I'm sorry, not the omegas. Sorry, I made a mistake. I meant theta. Where's my eraser? Okay. All right, so this is the theta, initial theta. And this is the theta and the later time. Okay, so if you connect these 2 points, the straight line, like this. The slope of that line is nothing but this angular velocity, right? This is delta theta over delta t. So this is delta t, and this is delta f. I'm sorry, delta theta. Delta theta over delta t gives you the slope of that red line there, which will be your angular velocity. Now, what if you look at this event within a shorter time frame? What if you pick this point here and then this as your initial and final data points? Point right there and then right there. Obviously, you'll need the slope of this line now for a shorter time interval, which is this. And you repeat this. And then again, one more time, until you can't do it anymore. But you end up with this tangent line. The slope of that line is the instantaneous angular velocity. So the slope of the tangent to the theta versus t plot at some time t, which is this t, gives you the instantaneous omega. All right. So we have the average angular velocity, we have the instantaneous angular velocity. That's right, instantaneous. And that's it. That's angular velocity. The next step is, what if this instantaneous velocity is also changing, right? Something like this. This is in seconds. This is in radians per seconds. But it's not a constant angular velocity itself. It's changing. So what do? We find the initial values and the final value for those two, omega and t. So delta omega divided by delta t, omega final minus omega initial, divided by t final over t initial. Okay, so here is t initial, here's t final, and the corresponding omega value. All right, in other words, again, the slope of the line that joins the 2 points here, from here to there. The slope of that line is what I just wrote here. Okay, and we define it as the average angular acceleration. The symbol is going to be alpha, average. Okay, alpha average. If I do it at a smaller time interval, I can find the instantaneous alpha, just like this one. Let's use the limit notation. Limit when delta t goes to 0, delta omega over delta t equals this, instantaneous acceleration. Okay, so omega was a vector quantity. So is alpha. Angular acceleration is also a vector. But which direction is it pointing at? Okay, so here you see this. So the directions should agree, at least linearly. This means that omega is also a vector along the perpendicular direction. But is it pointing up or down? Okay, so is it pointing up or down? Now that depends on what's happening to the angular velocity. Is it increasing as it is in here, or is it decreasing? All right, if it is increasing, if it is speeding up, if the rotation gets faster and faster, then the angular acceleration is parallel to omega. If it is slowing down, it is anti-parallel. Okay? If these two are parallel, it's speeding up. Speed up. If omega is up, but alpha is down, or omega down, alpha is up, if they point in the opposite directions, this means that the object is slowing down. Okay, so a downward alpha does not mean the object is spinning or rotating or going in circular motion in the opposite direction, or which is the clockwise direction. No, it is still going upward. So it may speed up, reach a maximum speed, and then start slowing down. While this is happening, you know, this picture here for omega and t may look something like this, right? Omega was 0 in the beginning, starts spinning, reach the maximum angular velocity, and then starts slowing down. But during the whole thing, it never changed direction. It was still spinning in the same direction. So omega as a vector was in the same direction, but what happened is when it was speeding up, alpha, the angular acceleration, was parallel to omega, and when it was slowing down, it was pointing in the opposite direction. All right, so that's the vector nature of these variables, the angular velocity and angular acceleration. This is the angular acceleration. All right, so we had tangential acceleration, radial or centripetal acceleration, and now we have angular acceleration. All right, you got to be really careful with the directions of these. So if you're here, okay, let's say you're speeding up, which means there's a tangential component of the acceleration this way, A10. Just because it's going in a circle, there's a radial component of the acceleration which points to the center. This is AR or AC. All right, and you can add these. You can add those and then find the total acceleration there that I mentioned in the previous video in part 2. So this would be the total acceleration vector there. Let me use the arrow, hang on. Total acceleration. Okay. Now these are all in the plane of the circle. But now we have this guy here. That's angular acceleration. Points up. All right? It points up when it's speeding up. If it slows down, things will be the other way around. A tangent will be anti-parallel to the velocity if it is slowing down, right? Okay, so that makes you wonder now. Okay, omega is a vector, alpha is a vector. Fine, this makes sense. But if I go here, if I put an arrow on top of omega right here, what about theta? Is theta a vector? Okay, it is. You know, there's no harm in attributing a direction to theta. Although visually it doesn't really mean much, because what we know is theta is just an angle on this plane with the circle here. But in general, for completeness, let's say, you can define theta to be a vector that points up like this. Okay, while the object is going in a circle like this. This is your position vector r, and this here is your velocity perpendicular to both r and theta. Okay, so these 3D vectors are perpendicular to each other. Another way to demonstrate them is using the right-hand rule again. Not this version, but the 3-finger version. As you see, the thumb, index finger, and the middle finger are all perpendicular to each other. Okay, each of these fingers are perpendicular to the other two. The other two will define a plane, and the third will be perpendicular. So it is possible to call theta a vector. Okay, so that's the vector nature of these variables. So what about the kinematics of it? Kinematics equations. Now, since you're familiar with linear motion, one-dimensional motion, and you know what happens if the acceleration is a constant, you know, you have equations. You're familiar with probably 4 equations. In some books, there are 5, but these are all related, so they're not independent. So let me summarize from, let's open the parentheses here. In the linear case, when A is a constant, the equations for displacement, velocity, and so on are given as follows. If the initial velocity is I, vi, multiplied by t, add a half a t squared. Okay, there's another way to write this. If you don't know what the acceleration is, but if you know what the initial and final velocities are, just add them up and divide by 2, therefore find the average and multiply it by t. Okay, that's also that delta x, displacement. Delta x is x final minus x initial, right? V final is V initial plus a times t. And there's another formula. If you don't know how much time elapsed, you can still find final velocity in terms of the initial velocity and acceleration and displacement. Vi squared plus 2a delta x. That's for linear. Okay. Now, in our case, for circular motion, we're going to replace these variables with their counterparts. For instance, x will become theta. V, velocity, will become omega. And instead of a, we're going to use alpha. All right, so delta theta will be omega I t plus 1/2 alpha t squared. Omega final will be omega initial plus alpha t, not a, but alpha t. Just better alpha, yeah. And then finally, omega final squared is equal to omega initial squared plus 2 alpha delta theta. So these are your, oh, there's one more. There's one more. That's for delta theta without the acceleration. Average angular velocity times t. Now, in some books, you may find 5 equations. That's when you write delta theta, not in terms of omega initial, but in terms of omega final and alpha. So let me include that just in case you see it somewhere. Okay. Or delta theta. And you can prove this. It's really easy to figure it out. Omega final times t minus 1/2 alpha t squared. Okay. You may see it in some book or Wikipedia or something. Okay. So that is, yeah, that is the kinematics equations and the vector nature of circular motion variables, vector quantities. Okay, right hand rule. Remember the right hand rule, not the left hand, but use your right hand, curl your fingers in the direction of rotation, and the thumb will tell you which way omega points at. You cannot find the direction of alpha with the right hand rule. Okay, I mean, omega can be up, but alpha can be up or down. It just depends on whether it's spinning faster or slower. Is it speeding up or slowing down? Okay? All right, so let me stop here.